Now, so this is section 7.2, and now we're looking at more general disks. I want to make sure that I mention the word disk, but put general in front of it, because this section's called the disk method, and then all of a sudden they say solids with known cross sections. Well, again, remember that when we started, we just said, well, okay, I've got this thing that I can think of as being made out of a bunch of disks, and that's pi r squared h for each disk. And but the pi r squared, that was just the base area, right? So here's my disk, here's the base area A, and that happens to be pi r squared, and then times h. Well, that's not special. If I take something like this and say that that's h, and then this is L, and that's W, something like that, well, the base area, right, A, is equal to length times width, and then we take the height times that to build up the volume. And so generally speaking, we take this base area times h. And so if I can tell you the base area for every single slice that I make of an object, then I could add all those up and get a volume. And so what they point that out, and they say, again, I find it slightly what's the word I want, demeaning or something like that, that they everything is a special case in this textbook, and I think you will be well served if you try not to look at them as special cases. So in general, if we want to find the volume of something where we can add up, and so we'll take a limit as our delta x, or more generally, I'm going to call it delta h, goes to 0. If we can add up a bunch of a sub i's times delta h sub i's, we can turn that into some sort of integral from an a to a b, and we'll get some a of h dh. Now, if we slice along the x-axis, then this is an integral of a of x dx. If we slice along the y-axis, this is some a of y dy. Okay, but every single time we are just trying to find representative area, cross-sectional area, that as we slice we can do that, and then multiply by some small height, and that height goes to 0. So we're starting to just talk about the slices themselves as opposed to the cheese wedge you end up with. So the pi r squared thing fits into this. Okay, so more generally, it doesn't have to be a round disk. It could be a square disk or something like that. A square washer. Any of those things work. Let's see. They give an example of a volume of the solid shown in figure 7.25. The base of the solid is the region bounded by the lines. Okay, so here's what they're doing in example 6 on page, what is that, 452. Okay, on there, they say, okay, here I have a triangular base, and this is 1 minus x over 2, and this is the negative of that, so x over 2 minus 1. Okay, and they call this one f of x. They call that one g of x. So there they have it, and then what they say is they're going to build a solid by making equilateral triangles. Okay, so they're going to come in here, and if I slice right there, then whatever that length is, so that length, I'm going to build a triangle that is L, L, and L. Okay, so the question is, well, do I know the area of that triangle? All right, so area of this, well, it's 1/2 height times base, I guess. That's one way to look at it. And, well, it's 1/2. I know the base is L. The height, oh, well, okay, we got to take a minute here. If I go perpendicular, so that's L, and that's L over 2, then by the Pythagorean theorem, I get L squared minus L squared over 4 for this. That's square root of that. So that's that height. And, well, that's 4 of these, so that's the square root. Let me write it here. The square root of 3L squared over 4, but if I take the square root of that 4, I get 2. And so then I can also take the square root of that L, and so my height is the square root of 3 over 2 times L. And so my area looks to be the square root of 3 over 4 L squared. Okay, so so that's my base. Okay, so I'm just going to add up a bunch of those. So I'm slicing this way, so I'm going to, I know I'm going to have a delta x, and each of my areas is going to be square root of 3 over 4 L squared. Okay, now what's L? What's that distance? Well, it is the top curve, f of x minus g of x. That's L. And so that's 1 minus x squared over 2 minus x squared, or x squared, 1 minus x over 2 minus x over 2 minus 1, which is, I got a minus and a minus on that, so I get 2, and then minus x. So this is 2 minus x. And I'll do an integral, and, well, it goes from 0 here, 0, I guess, to wherever these meet. Now, where do those meet? Well, that is when y equals 0. So I've got to check that out too. Right now, looking at the textbook, they've got all the answers for me, but I don't know what those are. So I have that x over 2 minus 1 would need to equal 0, or 1 minus x over 2 has to equal 0. And so this is x equals 2. And so that goes up to 2. And there we have it. We've got our base area times our height. And so, what the heck is that? I need to square it out, I guess. So I get the square root of 3 over 4, the integral from 0 to 2 of 4 minus 4x plus x squared dx. So this is the square root of 3 over 4, and we have 4x minus 2x squared plus x cubed over 3 from 0 to 2. Well, the 0 is not a problem. So we get the square root of 3 over 4. 4 times 2 is 8. 2 times 4 is 8. Well, that was convenient. Minus 8 over 3. And so those disappear. 8 over 4 is 2. And why do I have a minus here? Plus. So 8 over 3, well, 8 over 4 is 2. And so I get 2 times the square root of 3 over 3 when I multiply all that together. And there we go. That is our volume. Okay, and that is this general idea that they all of a sudden call manufacturing and so forth, but it is the same disk method. It's just our disk isn't round anymore. Okay, there we go.